Welcome to the morning session on Tuesday. We have 6 presentations. First presenters from Poland, Professor Bogdan Miedzinski, please.
Okay, thank you, Mr. Chairman, ladies and gentlemen. I think that not too many people as today, but it's obvious that means that yesterday we enjoyed very much. Okay, but thank you for coming here. Okay, my presentation title is indicated here and deal with the problem with detection and selection of ground fault in the network, middle voltage network, mostly in the middle voltage network which operated in mine, or open cast mine, which is very important things, with no effective earthing. The first is introduction, next the general concept and of the protection, sensitivity problems of the protection, shielding on three-phase cable load, interference, performance of the protection on the ground faults in real middle voltage networks, no effective grounding, and the conclusions. As I already mentioned, we have a real problem with the clearing faults in the ground, particularly when we have heavy resistive faults. Therefore, in this case, there's no way to detect it, since everything depends on the resistance or impedance of the loop through which the current is being flowed. And therefore, practically, it's impossible to detect it, especially if this faults of a small current value, even below 1 amps. Due to security, we have to switch off as quick as possible. Therefore, that's very difficult to do that. And therefore, we use different protections and different methods and different way of operation of middle voltage networks. You know that the networks with no effective earthing can work as isolated, can work with compensated, can work with grounded via resistance, and can work also via grounded by impedance. And also we call this is so-called is compensated with additionally forcing of active component, which improve the operation of ground fault protection. Therefore, we are looking for another possibility. There's no the problem of digital protection. Digital protection is a very good works, you know, but only if you have the physical quantity when you measure it. That's the main problem, is how to measure physical quantity. That's everything. Processing, digital processing is very easy, but the most serious problem is to detect this quantity, to measure this quantity as quickly as possible and with as high accuracy as is possible. We found out that one super problem as a choice can be used appropriate types of the current transmitters in the Hall sensor. Hall sensors for everybody is very clear what it is, and is widely used in the practice. And we found out on the basis of our experiments, which was done not only theoretically, but also we check it in a mine. And therefore, there is real possibility to construct such a sensitive switch. That's a very simple and can be easily adapted to the dimension of the power cable. Therefore, can be located directly on this. Here is the structure. The structure is very simple. There's a simplified scheme. As you see, that's the first is a core balance transformers, and for this case we don't use the residual current transformer. Residual current transformers were the 3 current transformers connected in parallel, but sensitivity is very poor. Therefore, the best is so-called, we call it core balance transformers, which sometimes we call Ferranti transformers. Therefore, that's this things is inside. This is a gap, and inside the gap is located Hall sensors. And Hall sensors is activated under the influence of the magnetic field, which is generated by the current flowing in this. This is a zero sequence component, which is, and then is polarized by the voltage. And the voltage, since it is directional protection, the voltage is used as the zero sequence voltage, which is taken from open delta unit of voltage transformers. That's activated units with fiber optics, whatever you wish. Therefore, it depends. You can use the wire or wireless transmission depending on the choice. However, here is already, I will explain you, is already inside. There's an additional core, which we call a screen. Just a moment, you will see, and also can be used additional windings that is also used to to supply independently this protection. As you see, the core is very flexible, is made of a sheet. Therefore, we are easily to clamp it on the cable, depending on that. Okay, therefore the principal operation is very simple, since this is based on the fact that we have a sine wave of a current and a sine wave of a voltage. Therefore, the flux, which is depicted here, is also indicated sine wave. Of course, include the high harmonics, and polarized current with proportional to the voltage. U0 is also sine wave. Therefore, the whole output of the whole is a product of these two quantities. That's the parameters you see factor depending on parameters of zero sequence filter, voltage filter, and Hall sensor respectively. Here, as a matter of fact, after the introduction, internal angle you see, and the transformation, we obtained these things. As a matter of fact, we have two components. The whole voltage is composed of a DC component and AC component, and we use a DC component, just only DC component. Therefore, since it's very difficult to consider the phase angle, therefore to calculate it, we compare the DC component to the maximum AC component, and this way we have a calculation of these things. One of the problems that I would like just only mention is a slight asymmetry of Hall sensors depending on the structure. Sometimes we have fluctuations of AC voltage. Okay, sorry. AC voltage, as you can see here. Therefore, however, since we use a DC, it doesn't disturb our work of these things. Also, that's very important is magnetic properties of the core balance transformers. In this way, we employ this magnetic materials. It is a cold rolled sheet, and that's a magnetizing curve, as you see here for this when we employ it. First, we check how high is the magnetic field intensity or flux density in the gap, which is just a moment, in the gap here. So therefore, we just make the analytical attempt to that. That's a magnetic flux line distribution for the 2D for the very small current I30, the 2 MEC, and the picture, the colorful picture for the same things. You see that there's some value of magnetic field intensity under which is located the sensor. And then next we consider the influence of the different parameters, geometrical parameters of a core balance transformer on magnetic flux intensity or density, and therefore depending in this way you can, oh sorry, okay, and this things this is not especially convenient to this. In these things you can find the flux density inside the air gap depending on the width of a core for this and this. For 50 amps, for example, you see that it doesn't depend yet. However, of course, this is what is obvious. It depends tremendously on the gap of the gap length. What is obvious? Next is we check the flux density within the gap area as a function of the unbalanced current. I mean the 3I0 for these parameters, and you can see that indicate the linear independence. Depending for this area, therefore this is linear, this is not linear, therefore we have also some problems here. Next problem is if the core balance transformer is too big with compared to the cable, therefore the location of the cable inside this inside the window of the core balance transformer can influence magnetic field intensity on flux density is here. Therefore we checked first, we theoretically consider what's going on. We have a different asymmetry and different location of the three-phase cable, and we check the value of magnetic field flux density or magnetic field intensity inside, and we found out that that is real problem. That's a real problem, since if we want to get the very sensitive protection, therefore we have to protect against this problem. Therefore, what we decided in this case to use additional screen. The cable is surrounded by the additional screen made of the same materials. And what is the influence of these things? You know, first we make a calculation, since it is symmetrical things. Therefore, we can consider it just only for the half of the system. That's, you see, in this way, there's a core balance transformer. The screen is a three phases respectively here. And then we consider that's a gap in which the sensor is being located. As a matter of fact, we found out that sensitivity, the magnetic flux density inside the core balance transformers in which the Hall sensor is exerted, depends, of course, of the thickness of these things. Therefore, this thickness like that, there's not any influence. There's not any influence about the D over DC. However, with increase of the thickness like that, we have some influence of that. Therefore, the more higher is the thickness of the screen. Therefore, the lower is the magnetic flux density. Therefore, sensitivity is being dropped down. However, if we compare S and R, signal noise ratio, we get a better relationship with the screen than without the screen. Therefore, the efficiency of operation is much better. If was already done, it was just calculated, then was investigated using the physical quantities. Therefore, we make investigations in real mine, copper mine conditions, and not copper mine by brown coal conditions. That's why this is network structures like this. It is supply, and here in this network you can see different level of middle voltage. For example, in this mine was 20 kilovolts and 6 kilovolts, and you know that if we have Y delta transformers, therefore delta act like a trap. Therefore, there's no way, there's no round for the current flowing there. Therefore, if we have a faults therefore the current is flowing just only this way. So, if you have a fault in the 6 kilovolt, the current is on independently. I'm talking about the ground, fault to the ground. In this case, for the 220 kilovolt, the networks operated with isolated neutral point, also with a grounded neutral point. However, for the 6 kilovolts, it was you see this was compensated with so-called the forcing of active component. What does it mean? That if we had a signal from the voltage, after 3 seconds, you know, this switch is being closed, and we include resistance. Therefore, we force additional resistive current value, which is very good for the active, protections, indicating active parameters. And then next. You see, that's indications of the measurement in real mine, and then in this case, you can see the picture for the. This is the fault. Fault is in this point. This ground fault. After 3 seconds, we have automatic forcing of active component forcing. Therefore, the current is being increased in this point. And as a matter of fact, immediately we have a picture. Here you can see that. For this way, then we have a compensated. However, the sensitivity of the whole sensor, this is the highest when there's no shift between the current and between the voltage. We have to use some shift, and then the shift is for this compensated must be 90 degrees. Therefore, in this case, when you see that even that we have a fault where we have no forcing of the active component, the value of DC component, the whole sensor is very little. And this moment is raised up to about 5 volts, and therefore that's here. And therefore, you see that for this system, after activation of ACV, the network, we are able to detect this fault easily. This is an example that you can see that for the 20 kilovolts, however, totally isolated for the current between 0.3 and 1.5 amps. That's very little current. It's very difficult to detect it. You see that the current for these things is the voltage DC is pretty good. It's about 2 volts, something like this. Is saturated to about 1 volt. Therefore, easily we can detect these faults. Here is an example show you the performance in the 6 kilovolts networks. This is absolutely similar, the same. As you see, this is the ground fault. There's an operation of ACTV. Current is being increased. You can compare it, and that's worked very good. And here you see that's operation, like you can see. This operation, there's a DC component, the whole that is for after the operation ACV. There's increase of current. These are like the step things in the current, this not force exactly the same. Probably the loop resistance is being changed, therefore once is increased a little bit and another is increased about the 20 amps. And here is the indication, since we located this protection not only on the photo lines, also on the healthy line, to compare what's going on the healthy line. On the healthy line, you see this, we also obtained the DC component, however, is negative. This blue line is, you see, there's a negative, since the current flow is just opposite direction. Therefore, you see that this protection we found it can work very good, provided that properly selected, properly designed. Any conclusions? There is a chance for use the Hall sensors as a sensing element of directional earth fault protection for medium voltage power network with no effective earthing, provided the proper selection of a new structure of a zero balance current transformer. At the criterion for protection, we use the DC component of a Hall voltage as a result of product sequence current and the voltage affecting the sensor. However, to increase resistance of the protection to internal electromagnetic fields interference, therefore of asymmetry of load as external interference, special magnetic screen must be applied. And investigations which were carried out under real ground fault protection of for different faults, solid earthing, high resistance up to about 2.5 kilo ohm. Earthing we perform it by dropping the line of the overhead line to the ground and allow to just freely allow the arc freely the things. Therefore, the current in this case was very little, and with high resistance up to about 2.0 kilo ohms and 6 kilovolt and 20 kilovolt distribution with no effective earthing, confirm applicability of this sensor. This protection is easy to use, maintained, and managed. Thank you. Thank you very much.
Thank you very much. Interesting presentation. Any questions? Yes, please.
I have one question. Generally, concerning the theory that clamping this high voltage cable, I'm just wondering, I guess this is relatively common methodology to use a clamp for that purpose. And generally, when using clamp, this is practically very similar to current transformer in the overall. So I'm wondering what is the advantage of this approach with Hall sensor, considering that we have seen that you had a problem with the position of cable and the flux distribution inside when you use finite element method to check it. And what is the comparison between this method with Hall sensor in contrast with, let's say, the current transformer approach?
Okay, thank you. I think that you know what is how it look like the Ferranti transformer. Ferranti transformer is big things like that, and the size of this, there's a big things. Therefore, we use very little, and we clamp it directly on the cable. Therefore, the magnetical coupling is as high as possible. We consider this asymmetry due to the situation when the window is a little bit bigger. Then, since not necessarily you have to use the Hall sensor protection for the particular cable. Sometimes you select it. That's the main advantage. That's absolutely the main advantage. That's all. That's all.
I have a question. Fault detection in a medium voltage network may be realized according to various criteria. It depends on the type of earthing, through resistance, through Peterson coil, or isolated. Is your method dedicated to the network with isolated neutral point, or maybe earthed through resistor?
Both. You know, that's only we have to use a phase shifter. This phase shifter was indicated here. Wait a moment. That's just a moment. Oh, this is a phase shifter. We have to change angle. Since sensitivity of Hall sensor is the highest when we have current. I mean, zero sequence current and the voltage in phase. However, for, as you well known, that it depends on the operation of neutral point. Yes, yes. Therefore, we have to shift about the 90 degrees. And of course, we compare the efficiency of that with the different types of protection. Overcurrent protection, delay time, admittance protection, everything. And we get that that seems to be the better.
Thank you very much.
Thank you.
Thank you.
Thank you. Okay.
next presenter is from Czech Republic, Mr. Vaclav Kolar.
Okay, Mr. Chairman, ladies and gentlemen, good day to you. My name is Tomas Mlcak. It's good. I am from VSB University, Technical University of Ostrava, of Czech Republic, Faculty of Electrical Engineering and Computer Science, and Department of Electrical Engineering. I introduced the article improving power quality with the use of a new method of serial active power filter control. The quality is still very discussed issue, and we three nonlinear loads in supply voltage distortion in distortion gate width is due gate in impedance. This picture show the main indicators of quality of electric energy. This is amplitude of power voltage, frequency for power supply network, voltage drops and overvoltage, harmonic distortion and flicker, and voltage asymmetry. In other picture show this hardware conception in this serial active power filter. This is converter. This converter is directly show this UC voltage, and this voltage sum with voltage from line US, and this is transformer. This sum with US voltage we have this voltage UL. This is filtration voltage. In other picture we have which we can be used the serial active power filter. We maybe compensate the voltage drops and from the power supply impedance. We symmetrate and regulate power supply voltage, filtration, harmonics. We maybe causes is US, the power outage, and we maybe regulate this phases shifter. In this we use some three methods. One method is Butterford filter, successive fourth order approximation, and fast Fourier transform, and new comparative method we developed with author. This is first method controlled by Butterford filter. We here first Clark transformation and other reverse Park transformation, and this is low pass Butterford filter fourth order, and then we have Park transformation and Clark transformation, and can calculate voltage for the converter for the power filter. This is equation for this model for microprocessor and by linear transformation. And this is second method. Second method is fast Fourier transform method. We sampling some values and calculate Fourier transform. We calculate these amplitudes, and now we have this UC signal for converter. This is fast Fourier transform from example from 4 point of discrete Fourier transform, and this is no good, and this is no better, because we must sampling this value, and after we calculate this distortion. It's some next time. It's here is other method. This is author's method. In author's method is comparative method. We have in microprocessor this sinusoidal wave, and we comparison this sinusoidal wave from this wave the phases. This is very good for a serial active power filter, because we now ended voltage. We have 327 voltage and 50 hertz. This is possible. This calculate directly. Here we can see pictures is from block diagram, connection, measuring, and control system. Here is phase loop loop. Here is voltage science. Here is block generate. This is block DC low voltage measure, and this is analog digital converter, and is block set pulses for this converter. This is signal microprocessor for control all system. We measure this with some distortion voltage. We take here some inductance, and here we destroy supply voltage. First from three phases rectified, and other is one phase is rectified. That's other example. Here is distortion voltage, and here is measure for this system, and we sum this UC in this system, and here is sinusoidal output for these loads. This picture show harmonics in the system when voltage distort by 3 phases rectifier and resistive inductive loads. This is total harmonic distortion from power supply, and this is total harmonic distortion from Butterford method and Fourier method and comparison method. Yes, this is show that this comparison method is the better, and here is some each harmonics from this measure. Yeah, this is waveform from this measure. Here is control using comparative method and inductive load, and input voltage is destroyed by 3 phases rectified. This is input voltage in the serial active power filter, and this is output voltage. This is control voltage for converter voltage you see, and this is show the same, and the voltage destroyed by single phases rectifier, and this is input voltage and output voltage. Here show some asymmetry, and each phases distorts other, and here is look here we can see output voltage from the serial active power filter. Yeah, in conclusion, we tried that this comparative method is the best method for using this this serial filter, and this serial filter we can use for extensive distribution geared, where we use this is low cost from this we building new network or new gear. We this use for off-grid systems, and some modified this we maybe used for some system which where we accumulate many energy, and then we cover system by voltage from serial active power filter. And now we testing some combination serial and shunt active power filter in hybrid filter, when shunt active power filter eliminate this first problem in this distortion in the system power voltage. Yeah, this is all. Thank you for your attention.
That's very interesting. But did you also perform the compensation of active power? Compensation to compensate reactive power, since you know that's not easy to do that when you have distorted current and voltage waveforms. And so far, the theory about the power is not fully understood. Mm-hmm. There are many different. Few years I had a presentation, invited paper, showing about the problems of the active power filter. That's please take care about
this reactive power. We must calculate this very many loads from this.
But it's not easy. It's not easy, you know. Please look at the literature, since the theory doesn't exist. So far, there's no
it don't have
explaining this
model, and we must calculate quickly from this situation.
No, it's not the problem of how speed it is. There's the problem how to do that. Nobody knows how to do that. There are few theories. We use one of the theories, Czarnecki, Professor Czarnecki, that is theory of instantaneous current theories. Therefore, since the reactive power, which is carried out by high harmonics, it doesn't complain. You know, that means that sometimes they explain that this energy is split sometime in the system. Therefore, it's not easy to use such a active power filter just for compensation reactive power when we have distorted current and this waveforms. Of course, we can filter everything, but another problem is the compensation.
Okay. Okay, thank you.
More questions? I have a question. Your filter is a serial filter. Could you say something about power losses and voltage drop in normal operation, because the filter is still in main circuit?
Yeah, we measure this efficiency of this filter, and this efficiency was in the 30 to 85%. You say that this filter not working in the nominal, but in working sometime in the 50–30%. This efficiency, this is other problem. This efficiency is lost. This cases. Yeah. Okay.
Thank you very much.
Okay. Thank you. Good night.
Is from Spain. Carlos Roncero-Clemente, please.
Well, thank you, Mr. Chairman, for your introduction. Thanks for coming to everyone. My name is Carlos Roncero. I come from Spain, but nowadays I'm working at the University of Lisbon in Unova University, and I'm going to present my work entitled New Operation Strategy for a Grid-Connected Three-Phase, Three-Level, Neutral Point Clamped Quasi-Sector Inverter based on power losses. The structure of the presentation will follow the next scheme. First of all, I will do an introduction in order to delimit our topic. After that, I will explain step by step the design of the grid-connected operation strategy of our power converter. After that, and once has been defined some guidelines, I will propose the operation strategy to be implemented, and to validate these ideas, a simulation study was performed with the discussion of the main result, and finally the conclusion and the future activities. Nowadays, it is well known that shortage of fossil fuel and the necessity of reducing CO2 emission, among other reasons, has significantly grown the number of inverter-based distributed generators connected to the low voltage distribution network. Many of these converters interact and perform as interface with renewable energy source like PV panels, wind turbine, and also they are presented in any energy storage system. One can assure that this power converter will play a major role in the future smart grid. Concurrently, industry and research are aiming at cost reduction of the overall energy conversion process, and some innovative ideas looks pretty interesting for the photovoltaic energy conversion system. Traditionally, this conversion process for photovoltaic energy has been composed by two-stage power converter, a DC-DC boost converter, and a traditional inverter, and some new topologies based on impedance source network can step up this input voltage in a single state by means of the shoot-through. The main problem is that the relatively youth of the impedance source inverter make the design of their controller stage complex, because we can see here how complex is the input stage where many poles are presented. In a grid-connected converter, basically must coexist an operational strategy for the AC side, the synchronization of the inverter, a DC-link voltage control method, and special modulation techniques for this particular family of inverter in order to embed the shoot-through stage into the normal ones. As basis idea, we started to develop a control strategy based on conventional synchronous generation principle, based on the well-known relationship between the active power and the frequency and the reactive power and the voltage. Based on the main equation and assuming that the angle between the generator voltage and the grid voltage is near to zero, is very small, we can determine that the degrees of freedom to regulate active power and reactive power is the delta angle and the generator voltage, and also the generator voltage is the degree of freedom for the reactive power. Making an analogy with the equation that governs our impedance source inverter, we can include new terms in the degrees of freedom, the shoot-through that is cycle, which can increase the generator voltage. And even if we use some special modulation techniques, which can include the third harmonic injection, we have also a new degree of freedom. So in order to discover or trying to look for the best magnitude to control, is necessary to establish some criteria. Our criteria will be based on the power losses, to minimize the power losses, but we have to assume some particular feature of this converter. For instance, the reference active power usually is given by a maximum power point tracking, and there are different approaches to generate the reference of the reactive power, for instance, to work with a constant power factor, or to maintain the voltage at the point of common coupling in certain values. Of course, we have to assure that the maximum rate current across the semiconductor must be respected. How to track the reference of the reactive power? As we have seen in the previous slide, we have different degrees of freedom, and we have divided the operation range depending on the input voltage. We have, for instance, that the input voltage can be higher than 650 volts, so we can or we have to work in back mode with our converter. When the input voltage is between those values, in this interval between 565 volts and 650 volts, we have to work in boost mode, and if the input voltage is even lower than 565 volts, the input voltage must be, the operation mode must be even the boost one. This control variable will be discussed based on the power losses. Here we have seen the main simulation result based on the power losses. For instance, we have here the main limit between the different intervals that is necessary to be studied. When the input voltage is higher than 650 volts, we have different combination. But according to the whole efficiency of the system, the best way to operate is without shoot-through, that is cycle, without shoot-through state, without third harmonic injection, and just modifying the modulation index. We will work with the highest values of the modulation index. In the next interval, it's necessary to boost the input voltage, because we cannot connect our system directly to a 325 peak volts distribution network. And the best way, the optimal way to operate is by injecting the maximum value of the third harmonic injection and also changing the modulation index. When we get this value, 491 volts, we cannot perform properly our system, and start to be necessary to boost the input voltage by means of the shoot-through stage, and we can see how the efficiency decreased in quite high weight. Adopted criteria based on this analysis is to minimize the power losses that are composed by switching, conduction, and turn on and turn off losses. Here we can see the implementation scheme of our power converter. We can see how with the delta angle we regulate with a simple integral controller the referent power, and the reactive referent power can be tracked by different approaches depending on the input voltage range that we can find. In the first case, when the input voltage is higher than 650 volts, the variable to control is the modulation index. In the next interval is also the modulation index, but we inject the maximum value of the third harmonic. And finally, we have to control the shoot-through duty cycle if the input voltage is lower than 550 volts to obtain the maximum boost capabilities. Here we can see the main switchings, the main signal in each modulation techniques without third harmonic injection and without shoot-through. Here without shoot-through and with third harmonic injection, and here with third harmonic injection and also shoot-through. Now we are going to present some simulation results that validate the previous operation strategy. We modify the reference in each, in both the active power and in the reactive power, and we can see how our system tracks properly the different reference. For instance, in second 2, we change the reference power from 2 kilowatts to 3 kilowatts, and in second 3, we change the reference of the reactive power from 0 to 0.5 kilovolt ampere reactive. This is the same test that we have done in any input voltage interval. In this case, we can remind that the control variable, the degree of freedom that we are controlling, is the modulation index and also the delta angle for the active power. Here we can see the evolution of both magnitudes, and here we can see a detail in this last time of this test, and we can see how the current is shifted in comparison with the grid voltage. The dieseling voltage is higher than 650 volts, and also the input current and the input voltage. We can see how the input voltage is working in continuous conduction mode. In this case, the results are quite similar. Our input voltage is located between those values, between 565 volts and lower than 650. And again, both reference of active power and the reference of reactive power are tracked successfully by means of the modulation index and the evolution of delta angle. And finally, in the most critical case, when the input voltage is lower than this value, in our case is around 490 volts, we can see how the system again tracks properly each reference, both the active power and the reactive power, by means of controlling the delta angle and the shoot-through duty cycle. Here we can see how the grid voltage is distorted because we have connected our system to a low voltage distribution network with a high impedance. The short circuit power of our grid is quite low, and we can see also this distortion is produced by the ripple in the shoot-through duty cycle, and this effect in the DC side are transferred to the AC side. This phenomena is quite common and is well reported in the literature. So in this case, we can assure that the system performs properly, but the quality is a little bit worse. As main conclusion of this work, with the proposed strategy, the overall system performed properly. Active power and reactive power response are coupled because the delta angle also, the generator voltage also affect to the generating active power, but we assume in the equation some assumption. When the shoot-through duty cycle is applied, output magnitude are distorted because this ripple and are transferred to the AC side, And further research will improve this control strategy mainly by using DQ reference frames in order to control DC magnitude. And of course, we are dealing right now with experimental work in the labs. Thank you very much for your attention, and if somebody has any question, please. Yeah.
Have you verified your stuff in laboratory condition, or is it still in modeling simulation stage?
Yes, we've already built some prototype, and we are starting right now with open loop test. We are just connecting the converter to passive loads and testing, for instance, the modulation techniques, and the next step will be the synchronization with the grid connection, with the grid, and step by step we will try to validate this strategy and other more that we have already proposed and developed in a real system, at a nominal condition as well.
More questions? Thank you very much.
You are welcome.
Next presenter is from Poland, Mr. Joachim Pielot. Sergiusz Boron. Sergiusz Boron, yes. Sorry.
Thank you for the introduction, ladies and gentlemen. I represent Faculty of Mining and Geology from Silesian University of Technology in Gliwice, Poland, and the title of our work is Empirical Model of a Human Body Resistance at a hand-to-hand DC flow. Just shortly the presentation plan. After the introduction, I will present the aim of our research, how we measured human body resistance, what model we implemented of body impedance, or we should say resistance, because we are talking about DC current. We identified the parameters of the model. It was used to evaluate later the maximum shock duration depending on the resistance, depending on the touch voltage, and at the end I will present some conclusions. It's well known that DC electric shock is less harmful than electric shock from alternating current. The number of accidents after DC electric shock is much lower. That's not only because it's less harmful, but especially it's the applications of DC are much less common than of alternating current. However, the number of DC application increases also for non-qualified users. I mean photovoltaic systems, which are widely used, especially in some countries. Power converters, electric traction. As I mentioned, I work in Faculty of Mining and Geology. The application of power converters is increasing in underground coal mines with DC intermediate circuit, sometimes very long. Also electric traction, it causes a lot of problems because the trolley wire is relatively low. It's about 2 meters, 20 centimeters above the ground. So there are some accidents because of touching trolley wire. So we can say that the hazard of DC shocks is rising. The main two factors affecting the effects of electric shock is, of course, the duration of the shock and the magnitude of touch current. The touch current depends on the touch voltage and resistance of the shocking circuit, the whole shocking circuit. Especially in this shocking circuit, we can find two main resistances. It's the body resistance and stand resistance, I mean shoes and floor, etc. Of course, also the type of the current is important. When we are talking about AC current, frequency is important. I mentioned that because in our future plans, now we concentrated on the DC current. we want to do similar investigations for high frequency AC currents. Important is the current pathway through the body and of course physiological condition of a human. There are differences between individual humans as far as the body resistance is concerned, as far as the effects of electric shock are concerned. The aim of research was first to select a model for human body impedance. We have a lot of models described in the literature. We selected one of the models. Then, as I said, we identified the parameters of this model, and we found a correlation between maximum allowable duration of the shock and the touch voltage. It can be important from the requirements for means of protections point of view. For example, automatic disconnection of the supply. The time the supply should be disconnected after the fault when we have touch voltage, for example, on exposed conductive parts. The first model we found was in IEC 479 report, effects of the current on human beings and livestock. This model consists of series of impedances, impedance of the skin and the internal impedance of the body. Of course, the impedance, especially impedance of the skin or the resistance of the skin, depends on the voltage. We use another model which was described by Professor Korniluk from Poland. In some ways it's similar. We have this internal resistance and we have the impedance of the skin. Especially here it's worth to see this resistance depends on the touch voltage in exponent way. For the DC application, we simplified this model. Internal resistance, the skin resistance depending on the voltage, and the capacitance only for transient states. This is our laboratory stand. This is how it looked like. It's already prepared to do investigations of AC high frequency currents. We have voltage sources. These are two plain electrodes which were touched with hands with open palms. To keep the force of the contact constant, we used a digital scale. Then we have some recording system and measuring instruments. This is one of my colleagues, which was the subject of one of the subjects of the tests, and the subject was standing on the insulating matting to prevent the current flowing to the ground. And this is the block diagram of our measuring system. These are measurement results of touch current against the touch voltage for 3 different subjects, 3 males in the age of 40-50 years old. And we try to, this is values of resistance, measured resistance. We can see that, of course, the touch current is not non-linear to the voltage, and it means that, of course, the body resistance goes down as the touch voltage goes up. And we try to approximate values of the resistance. We use this mathematical description of the relationship between the body resistance and touch voltage. Here we see the touch voltage and the exponent. We try to find, we have 3 variables here, this coefficient, this exponent, and internal resistance of human body. The criterion we used to find these parameters was minimizing the residual variance. The variables are listed here. We have the problems with internal resistance because the best fit or the minimum value of residual variance was for internal resistance over 2.5 kilo ohms, while we know from the literature from other investigations that internal resistance of human body is much less. It's about 0.8 kilo ohms, and for this reason we limited the variation of internal resistance to this range, adapting the boundary confidence level. So it meant that the maximum value of internal resistance was just above 1 kilo ohm. The minimum value was just below 0.5 kilo ohms. So after this limitation, we found these variables, and these are the lines of approximation. The tests were conducted to maximum 80 volts touch voltage. Of course, it was for safety reasons. We extrapolated these values to higher voltages. These are values of body resistance up to 80 volts. After extrapolation for higher values, we obtained these lines. Of course, it's always difficult to test on live humans the higher voltages. It's difficult to find volunteers for this test. So, but the real danger, of course, is in this higher voltages. And this is the same for the touch current against touch voltage, and incorporating these curves into IEC time current zones, like here. These are well-known diagrams showing the effects of electric shock for different touch current and different electric shock. We obtained, and of course we have to take into account the fact that the resistance was measured along hand-to-hand pathway. The worst effects of electric shock, the ventricular fibrillation, is when the current flows from, for example, from hands to the feet. So we took into account the heart current factor 0.4, which means that the current pathway from the hand to the ground is about 2.5 more dangerous. We obtained the diagram of maximum shock duration against touch voltage for the hand-to-hand, left hand, right hand pathway. As you can see, this is in milliseconds. The voltage about for this blue line, the lowest body resistance, about 650 volts and 1 second. This is the maximum permissible shock time. Of course, for other subjects, this extrapolated curves were for higher voltages, but we always have to take into account the minimum body resistance. Okay, so let's go to the conclusions. We found out that the resistance of human body can be modeled using the impedance model proposed by Korniluk, and the analytical form was presented previously in the form of equations. Of course, we saw big differences between the models. They result from different physiological characteristics of test objects, of individuals. We extrapolated the experimental data to determine the human body resistance at higher voltages. It can be strange. We are talking about voltages of 600 volts, 1000 volts. Of course, the basic criterion we used was ventricular fibrillation. The touch current can cause, of course, other harmful effects, for example, burns, especially when the duration of the shock is much higher. So we cannot say that 650 volts for 1 second is completely safe. Of course, it's not. These experiments have been carried out in the laboratory. The conditions were good, the skin was dry. In other environmental conditions, especially, for example, at underground coal mines, where it's a lot of heat and the humidity, the values of the body resistance, especially skin resistance, can be much lower. Of course, for different paths of touch current, effects can be different, and values of the body resistance can be different. The results we obtained can be useful for evaluation of requirements for protection means, and as I said, the next stage of research will be to find a model of human body impedance, this time for high frequency touch currents. That's all. Thank you very much.
I have a question. I'm sure that you know the IEC report effect of current to human beings and livestock part 1 and part 2. I'm sure that you compared your results with the results presented in this report. Could you indicate main differences between your results and results included in this report? The most important.
Yes, it's difficult to compare directly because we tested only 3 individuals, while this data in IEC report, especially the resistance versus voltage curve, have been carried out on much wider group, and there are some 3 curves I don't have now for different percentage of population. Our results were inside this curve, so there was no big differences, but as I said, it's only a preparation. This is the first stage of the work. We wanted to find a model, and now we, after confirming that this model is okay, we will use it for another research.
Thank you very much.
Thank you.
Just
yes,
just a little question, but only comment. It's a very important thing, since nowadays, as you know, it is recommended to use in the home the 2 separate installations, one AC and another DC, since to avoid the losses due to converters, when you have, for example, the solar battery, something like that, to avoid the conversion from the DC to AC and supply directly the loads which is used for DC load, like lamps, something like the LEDs, something like this, that will be probably in the future, the old building, new building would be already equipped with 2 installations. Therefore, your work is of great importance.
Yes, so as I said, the DC applications are rising, and of course the hazards also will rise. Thank you very much.
Yes. Next presenter is from Czech Republic, Mr. Jakub Tal.
Good morning, gentlemen. The topic of my presentation is peak-to-peak current minimization by differential evolution optimization. My name is Jakub Tala, and I am from University of West Bohemia, from Department of Regional Innovation Center for Electrical Engineering, from Faculty of Electrical Engineering. This is my presentation outline. I will start with our research motivation, which was motivated by our customer requirements, which wants current source injector for automatic Peterson coil tuning. Then the presentation will continue with differential evolution optimization of injector reference current. Then I will present the simulation and experimental results, and finally I will talk about something about conclusions. So as I mentioned before, we have some customer which wants from us some current source injector for automatic Peterson coil tuning. This current source should have maximal amplitude of current of 5 amperes, root mean square, which should contain some preselected current frequencies, some preselected current harmonics for grid-to-ground impedance identification for automatic Petersen coil tuning. The other requirements from our customer was small series price lower than 1200 euros, small device volume lower than 6 liters, and also our current source injector should work to up to AC voltage 160 volts root mean square. The current frequencies range should be between 15 Hz to 130 Hz. So how does it look like? This is medium voltage network with lower voltage size connected in star. The central point of star is connected over Petersen coil to the grounding, and we are connected with our injector in parallel to auxiliary winding of the Petersen coil. This is our injector with filtering inductance, and we are measuring output injector current and output injector voltage, and we are calculating some admittances. I will talk about this in the next steps. Actually, the H-bridge inverter or injector is based on single-phase H-bridge inverter with fast IGBT transistors. Final application will consist of silicon carbide transistors. Filtering inductance is actually, and it should be also in the final application, 750 microhenry, and all switching frequency is up to average switching frequency, because we use analog hysteresis control of current, is around 80 kilohertz. So we have relatively large losses in the core of this filtering inductance, and our DC link capacitor is around 2 millifarads with 400 voltage on the DC side capacity, and we are control the DC voltage by there is not drone, but here is chopper which controls our DC voltage to 340 volts maximally. If there is some ground connection, we are switching off our injector, because it's not necessary to inject some harmonics to the grid network if there is any grid to ground connection, phase to ground connection. So to minimize price and inverter volume, we focused also on peak-to-peak current, which was generated by our injector, and that's what is about our paper. So it was about minimization of peak-to-peak current, which affects mainly, of course, selection of transistors, and of course the core of filtering inductance. How does it work? We inject several harmonics, up to 12 harmonics simultaneously to the auxiliary winding of Petersen coil with the same amplitude, and if the Petersen coil is properly tuned and these harmonics are properly selected to be covered by this equation, we have the symmetric response. So this is results that injected currents with the same amplitudes and properly selected current harmonics will have the symmetric voltage response when the Petersen coil is properly tuned. So this is one possible solution how to tune the Petersen coil, by moving the core of the Petersen coil. Or we can use the direct computation method. We can, from two admittances computed from voltage and current. We can compute directly Petersen coil inductance, grid to ground capacity, or for example, grid to ground resistance. This is how our injector control and measurement scheme looks like. We have some processor. It's based on Texas Instruments processor with single point precision unit F28335. We are measuring, as I mentioned before, output current and output voltage of inverter. Then these values are filtered by low pass first order Butterworth filter, analog filters, and these values are measured by analog digital converters and by algorithm of by citing DFT, citing discrete Fourier transform. We compute the spectra of currents and of voltages, and we send these values to Petersen coil supervisor controller over RS485 bus. And the Petersen coil supervisor controller moves with Petersen core to achieve the resonance on 50 Hz with grid to ground capacity. As I mentioned before, the current of our injector is controlled by analog hysteresis controller, and the reference for analog injector for analog hysteresis controller was calculated from processor, and by digital analog converter is set it to hysteresis analog controller. So we inject up to 12 harmonics. As I mentioned before, we want to minimize peak-to-peak current. We use, this is a problem of global optimization in the real space. We are looking for the best phases of these harmonics to achieve minimal peak-to-peak. I will talk about it later. And for this real value problem, real value global optimization problem, we chose differential evolution, which is well-known method and very good method for real spaces problems. This is how the differential evolution works. We have some initial population. I will talk about these blocks later, but briefly, we have some initial population. We calculate the fitness evaluation. For us, it's peak-to-peak value. We select some possible candidates. We mutate them. We make some crossover and repeat this process several times. And after we find the best, we use the best founded values to use it for current generation. So this is a mathematical description of our problem. We have some of sinusoidals, and we are looking for thetas of the sinusoidals to achieve minimal peak-to-peak of course, for all time. We made the numerical approximation of this problem. So we minimized in our cases for 12 harmonics, we minimized 12 harmonics, 12 thetas. We are looking for 12 thetas which are minimizing peak-to-peak for some time with some discrete step calculation of this fitness function. And this fitness function is used for evaluated or results for our population of solutions. This is how the initial population looks like. We have some thetas randomly generated, and we calculate for them the fitness function. It was the first step. Then how the evolution looks like. When we took two random vectors of our solutions. We subtract them from each other, multiply by some mutation constant, and add it to some another random selected candidate, and this is our new candidate. The crossover is so this is how does it looks like. Or crossover, we select some parts or only some thetas, which will change with the previous population, which will be changed only with previous populations, and then we make selection. If the new solution is better than the previous one, we change the previous solution with the new one. This is how our simulation results looks like. This is so we our signal, for example, in this case, contains 12 harmonics. This is the frequencies of our harmonics. Of course, the worst case when all harmonics has amplitude 1 was 12 amperes. With initial 0 phases for all these sinusoidals, the result will have 8.94 amperes, and after differential evolution optimization, the maximum peak amplitude was reduced to 4.62 amperes. So this is how the reference current looks like before optimization, and this is how the reference current looks like after optimization. This is how our progress looks like of the best maximal amplitude. How it takes approximately 4 minutes in the computer. We have also some simulation experimental results. Which was measured on Peterson coil, which was connected in parallel with capacitor. Peterson coil was tuned to 168 millihenries. It corresponds to 230 amperes, and parallel capacitor, which emulates the grid-to-ground capacitance, was 58 microfarads. Here you can see some results, how the converter voltage looks like. This is the blue one. Peterson coil primary voltage looks like. Peterson coil primary current is the pink one, and injector current is the green one. Injector current corresponds to our previously founded solution for optimal settings of current harmonics. This is how our voltage response looks like. So the Peterson coil was properly tuned in this case. The parallel resonance is the harmonics was the symmetry of voltage response was achieved, and how our injector current looks like. So this is we generate the constant current for all frequencies. So this is my conclusion. So the paper presents the new solution for automatic Peterson coil tuning. The paper was mainly focused on optimization of phases of reference current harmonics, which was generated by injector simultaneously. And these maximal peak currents play a key role in converter design, such as transistor selection, whole converter size and price, which we want to minimize. The maximal peak current for selected frequencies was reduced up to 2 times from initial set of harmonics phases, and the solution was programmed in Visual Studio C++ for customer usage. So that's everything.
In fact, we have no time for questions. Maybe on the one fast question. Yes?
I have a question concerning that you have used sliding window DFT. What is your experience regarding the accumulation of arithmetic error, and the second is the problem of stability of the sliding window DFT?
Yes, thank you for your question. It's an interesting question. We are using 2 separate sliding DFTs with 2 separate spectral components, and we are resetting which are working on the same frequency, and we are switching between them. And we firstly reset the first one. We are using the result from the second one, After some while, of course, during the time, the errors are accumulated in the spectra, and we are resetting the second one, and we are using the results from the first one. So we are simultaneously changing these two signing DFTs out.
Okay, thank you.
Thank you. The last presenter, not least, is from Latvia, Gennady Miedzinski. Please compress your presentation. It's not possible because thank you. Short time.
Thank you, Shaman. Good morning, dear colleagues. My work is called Problem of an Estimation of the Wang generates economic efficiency in Latvia. This is not global problem. Please don't wait on revolution. But every little problem is a problem when you must pay it. So the aims of this research was to present a method for the win-to-bind financial efficiency evaluation. At the main part, to define parameters that depend on this evaluation at particular case. This is microgrid with one win-to-bind and some load and AC grid. So there are power relations. Win-to-bind produce average power PW, average annual average power. The part of this power is consumed by load, annual average load power, and second part is can be transmitted to conventional AC grid. So what? Wind turbine producing average power is characterized with the capacity factor alpha, which is the ratio of average power to the rated one. Part of the average power should pass to the local grid consumers, an average consumed power of which can be characterized with indicator beta. So load average power divided by wind average power. Total construction price of wind power plant is C plant. So C kilowatt is installation outcomes of 1 kilowatt. Installed power of plant including power converters loss costs. K with index A, reduction factor for cost of installed power. So very simple. The annual financial efficiency wind plant generation is here. So price of 1 kilowatt hour. There is outcomes for installation, coefficients, and capacity factor. So globally, dependence of an apartment price of wind generator power on the capacity factor and installation resistance is here. So it's very simple, but there is a problem with loss. How consumer can get compensation for power, for energy which is transmitted to conventional grid. In theory, it's possible to conduct net metering, or in other words, to transfer the produced electricity to the power network and use it again when it is required. Therefore, in Latvia is used a net payment system which is applied for microgenerators. In practice, the electricity costs for 1 kilowatt hour of each Latvian household consists of 3 main components. The distribution operator service CDOS, not a Microsoft DOS, just DOS. The mandatory procurement component CMPC, and the payment for the electricity CPE. Payment for electricity constitutes only 40% of the total cost for kilowatt hour. For household producing their own electricity from renewable sources, it's possible to save on account of the less component. Each household must pay for operator service and MPC, 60% of the total cost for kilowatt hour. This payment depends on energy received from the conventional grid. So if you get something from conventional grid, you pay. Your payment will be greater than 0, depending if you give your energy to conventional grid or not. Payment for the electricity is calculated by the net principle. So I called it E-balance, the amount of electrical energy for which household must pay in kilowatt hours. So it is difference from energy received from grid and energy transferred to the grid, or it is difference from between energy consumed by load and energy generated by the wind turbine. Total payment for electrical energy, DOS and MPC is so I called it for total equivalent amount of electrical energy equal, for which household must pay in kilowatt hours. And this E-balance, which is amount of energy for which we must pay, this amount of energy cannot be less than 0 within 1 calendar year. Energy received from the grid is E load and C wind consumed. This is a wind turbine generated energy consumed by load directly without transferring to grid. And here is household payment estimation. So equivalent energy can be expressed as function of three variables: load energy, generated energy, and consumed wind energy. If we have a constant load, equivalent energy can be presented as function of two variables, only two. For simplification of the diagram, all parameters were specified to range from 0 to 1, and load consumes 1 kilowatt hour. So we can see this diagram. So what? If we produce 1 kilowatt hour of energy with our wind turbine, this generation can be passed when we need this energy for our loads, and when we give this energy to transfer to conventional grid. So our equivalent energy depends on wind. When we have sufficient wind speed for generation necessary amount of energy, we can introduce wind energy generation indicator, beta E, and next indicator, the wind energy direct utilization indicator, shows which part of generated by wind turbine energy is used by load directly without transferring to the grid. Consumed wind energy divided by generated wind energy. And this is this indicator used in diagram. Equivalent energy as function of generated wind energy and wind energy generation indicator. So dependence is not linear. So total equivalent amount of electrical energy for which household must pay depends on energy amount generated by wind turbine and energy amount used by consumer directly without transfer to a conventional grid. For modeling was used a load and wind process were used. So load consumes 2.1 kilowatt hour. First or second wind profiles are the same according to energy, but not the same according to power. Third and fourth wind profiles are less than load profile, and next is greater than load profile, but not the same as moment power. Here is energy relations in the system at various wind profiles and constant load. We need one parameters, E equivalent. So if shortly we pay nothing, only in ideal case when consumed energy, wind energy divided by load energy is 1. When wind turbine completely covers load requirements in the same time when load needs the power. If beta E less than 1, in this case consumer can save on the account the rest of energy, but only within 1 calendar year. Therefore, this option creates obstacles for evaluation of wind turbine economic efficiency at long period, some years. The smallest equivalent energy value can be reached at the whenever possible bigger generated wind energy and directly consumed wind energy values. So conclusions. Annual cost and wind energy price depend on capacity factor as well on ratio of energy consumed by load to the energy generated by wind turbine. The amount of directly used wind energy depends on probabilistic distribution of the energy consumption and generation on the wind speed. Independence on conventional grid operator regulations and electric energy payment system, the owner of the wind turbine can get a compensation for energy transferred to the grid. But to describe the financial efficiency of the wind turbine, the indicator E equal was used. The smallest value of the equivalent energy can be reached at the maximum possible energy amount generated by wind turbine and energy amount directly consumed by load. To decrease household payments, it's possible to use load control. For example, some loads can be switched on when wind speed is sufficient for necessary energy generation. In each case, deep analysis on the household loads is needed. So, thank you for attention.
Thank you very much.
Maybe you can do something.
No question. This session is closed. Thank
you.
Very much.